let's say in the first part of the first lecture. That what we suggested is the group of conformal transformations. For the conformal theory in the dimension, we proved that it was O to D. And so when I mentioned something in the first lecture, and one reason that conformal theories have become interesting and important is that they give us a particular non-perturbed formulation of quantum gravity in particular geometry. And the simplest way is for the schematic, but it's kind of the sanity check that idiocy makes sense, is that this guy can also be interpreted as a symmetry of a curved manifold. It's called D-dimension, D plus one dimensional anti-de Sitter space. By the way, it is the maximally symmetric space, so the space that has maximal symmetry in D plus one dimension with negative cosmological constant. And the basic kind of kinematics of this idiosyncratic correspondence tells you that you have a space that near the boundary. So think of this space as having a boundary. And near the boundary, the geometry approaches this idiosyncratic space. So this means that I have more time to explain more carefully what this means. But this means that you have a geometry that is asymptotic to anti-de space. Inside, you can do whatever well things can that are allowed by quantum gravity. That represents a asymptotic. And the statement is that the Hilbert space of quantum gravity in with this asymptotic geometry fits into representations of the isometric group of ADS, which precisely for D, which also happens to be, so you have here ADS, okay, let's look at asymptotic ADS D plus 1, and the boundary has P and D, which also is the way in which operator or states, we will see, of a conformal theory also fit into representations of D. So sometimes you have a one-to-one correspondence between the Hilbert space of the conformal theory and the Hilbert space in symptotic ADS. And just as a cartoon, just to motivate, I think you may have an ADS course later in the year. But typically what happens is that imagine you are near the boundary and you insert one of these operators we were discussing that we were interested in computing the correlation function of. So this is the boundary theory, this is the bulk. So you insert a few operators. And physically what this does is this creates some kind of excitation in the bulk. Imagine like a graviton, the bulk. And then you have a one-to-one correspondence between bulk excitations. Say, a simple example would be just take empty ADS space with a few gravitons floating around. This is described in the boundary safety by a certain insertion of operator in the boundary that kind of inject some graviton into the bulk. And this is kind of the base of it. Okay, so you could spend 3 just on this. So just to give you a flavor of where this object also appears in theoretical physics. It appears as the isometries of this. But notice that the correspondence between the conformal group in D dimension and the isometric group in D plus 1 dimension. And that's this kind of corresponds between a bulk D plus 1 dimensional theory and a boundary D dimensional theory. It's called holographic. Here we won't spend a lot of time, but I just wanted to mention this so that apart from just exhibiting this guy, so that this guy connects with other things. Okay. So that's one thing I want to say. Something else or something else? Yeah. Another thing I wanted to say that is also kind of important, especially when we discuss several new topics, hopefully, this week. One of them having to do with conformal anomalies, essentially the failure of conformal field theory to be realized. So there's that you think that you classically have a symmetry, but actually quantum mechanically it's broken. We will see that this gives rise to interesting charges that constrain heavily the type of RG flows that can appear between theories. Remember, we were discussing these RG flows from a CFT in the ultraviolet and CFT in the infrared. And precisely the existence of conformal anomalies will give us a handle on what kind of flows are possible between conformal field theories. So, for example, just by using that quantity, you may imagine you have several CFTs. You may wonder, is there a way of flowing from a given CFT to a different one? And using this quantity that appears in the context of anomalies will allow you to say that there are certain flows that cannot occur. Okay, so it's a very strong bound of what kind of monsters can appear in the infrared. Okay. So the thing I want to discuss a little bit is the idea of this is not only pertinent to conformal field theory, but you can imagine the following thing. You can imagine taking a quantum field theory and coupling it to gravity. So far, we're studying field theory in a fixed Minkowski state, and now you can imagine coupling it to gravity. Just like when you have a global symmetry, like a flavor symmetry, you can couple the theory to background gauge state. Okay? So you can have a minimal coupling. So you have a global symmetry. Equal by a current, J mu, that's conserved. You can couple this quantum field theory to fields, so background fields that will couple to this current. So, and the minimal coupling you will find is that you can add to your theory a coupling of the type A mu, J mu. Okay? Where A mu is a background field that may not have any dynamics, it's just some background field that you turn on, and that allows you to study in particular, in a convenient way, what are the correlation functions of this current by studying the partition function of the theory as a function. This is related to what I said also the other day, you can compute this object. And this will give you a generating functional. So this will be a function of mu. And this object encodes the correlation functions of the current. Similarly, you can couple a quantum field theory to Kerr space essentially through the stress energy tensor. So you can add a coupling like this of this type. Okay? And I think you all have a feeling of how, if I give you a theory in flat space, I think you would know how to write down, if this theory has a Lagrangian description, you would know how to make it coupled to a Lagrangian metric and make it in a deep invariant way. Okay, so this is not something very mysterious. Okay, so another useful perspective on conformal field theories is to say the following. Is that, or about conformal, let me talk about, before we talk about conformal field theories, let me talk about one way of thinking about a conformal transformation in flat space on a fixed background. So first, once you introduce a dynamical metric, you can define what's called a wild transformation. But this is a transformation. Okay, I'm going to write it. No, I'm going to write the finite form. Where you take a metric, and all that it does is rescale the metric by some factor. Notice that this is not a diffeomorphism, just a local rescaling of the metric by an arbitrary, completely arbitrary function sigma x. Okay. This transformation is has the property of that it preserves the causal structure of your space-time. And that's why, for example, it's very important, it's very often used when you have a space-time and you want to understand what the causal structure is. Namely, if you want to know whether two points are causally connected, and you don't care about distances, again, because this doesn't preserve distances, right? What you do is you, for example, construct what's called a Penrose diagram of your space-time. And the way you do it is by doing such a wild transformation. Essentially, you are just, it's an object that is blind to distances, but only cares about the causal structure, which is preserved by this transformation. Okay. So a wild transformation can also act on fields in space-time. And if you have a field that has wild charge W, it will transform like that, for example. Notice that this transformation maps a metric to different metric. In particular, if you start with a metric that was flat, this will no longer be flat. Okay? Because mapping manifolds that have different geometrical properties. One can be flat, one can be curved. Okay?
A wild transformation doesn't do anything to the coordinates, though, right?
Yes, that's okay. Doesn't do anything to the coordinates. So, for example, I mean, to show that it's something that you more or less know, you can write down very easily. Again, I don't like, for this course, Lagrange is not important, but let me use an example of Lagrange of a theory of a free-scalar field. So if you tune to the coefficient, you did. So here's a theory that is invariant under wild transformation. So if you transform the metric in this way and you rescale the field with W equals d minus 2 over 2, this theory is wild invariant. Notice that this theory, if I go to in the flat space limit, you're just going to recover the theory of free massless scalar field. Okay? So what's the point of this regression? The point is that, well, one point, there are many points, but one point, and I don't have time to go through all of them because I want to move on to some other things. But the main point I want to say is that yesterday we derived the conformal Killing vector equation. And now I want to provide you a different perspective of what the conformal transformation is from this point of view. So what you can think about a conformal transformation that we were discussing yesterday is the following. What you do is you do a wild transformation. This changes the metric. Okay? But in order to talk about the symmetry, there's not quite a symmetry because you went from one space-time to different space-times. So there's a relation between the two space-times. To make it a symmetry, what now you can ask is there a diffeomorphism that will bring me back to my original space-time? And then you have a transformation, a combination of two transformations that map you one space-time to itself. And that you would call a symmetry. And to see how the Killing equation will come from this point of view, let me just formalize what I just said. Conformal transformation can be thought in the following sense, in the following form. First we do infinite, I could also do finite, but let's not worry about that. I want to do the Killing equation, not. First we do an infinitesimal wild transformation, and you ask, can I do a compensating diffeomorphism such that the metric is invariant? Okay. At the level of form, this means that it means this. So here I did a infinitesimal wild transformation. Okay, I do an infinitesimal detail. If I can find such transformations, then I map my spacetime to myself. Okay. And now we can just check that this is precisely given the Killing equation, the conformal Killing vector equation. Because all I have to solve is the equation whose is Jimino. This guy, remember, under the diffeomorphism, this is my okay, if I do a diffeomorphism x plus theta, then this guy is just minus the Lie derivative with respect to the vector field from the metric, which remember was what? Minus. Notice now I'm doing an arbitrary spacetime. Okay? So and this is precisely the conformal Killing vector equation. So this is a different perspective that will be also very useful when we study conformal field theories and we map them between flat space and the cylinder and so on. And there was also something else I wanted to say. Yeah, something else that you can also say is that, for example, you were asking before what manifolds have conformal Killing vectors. So I think that you can now try to prove that imagine you know the Killing vectors in a given manifold. Then you know the Killing vectors on any manifold that's conformally related to it, because what it's easy to show in this equation is that this equation is well invariant. So the conformal equation is well invariant. So if I transform the metric in this way, and I transform the vector field in some way, charge 1, then this equation is well invariant. So this allows you, for example, to construct the conformal Killing vector from the sphere, which would be a complete nightmare. In terms of the conformal Killing vectors, flat space just by doing it as well. Okay.
So, is it clear that a conformal transformation is a violent transformation plus it, and then composed with a diff derivative?
Yes. What is what this is essentially the.
Yeah, so that's equivalent to the conformal Killing equation, but is that equivalent to a conformal transformation? A general conformal transformation?
Yes.
Or an infinitesimal one?
I don't know. I could write the finance form of this if you wanted. Yes. I could write. I mean, I can write it. So.
Okay. I can look it up on my own.
I think that. Yeah. So here I just wrote the decimal version not to have parts of the limited world with the rest. Just physically write the following equation. Right. You have a metric, and ask. Let me do 2 consecutive transformations on this metric. Let me do first the wild transformation and then a diffeomorphism.
Okay.
Is that equation the same?
Yeah.
And if you put the fields in the right place,
yeah, it's just.
you will succeed.
Yeah.
Given the existence of control.
But it, yeah. Okay, so more generally, when we study conformal field theory, we will be, remember that I defined that generating functional, the partition function. So this was a way of defining a partition function or generating function of all of the correlation functions in the conformal field theory. All AI are operated on J or star. Now something that you can do is to upgrade this to an arbitrary metric. I think you will know how to do this. Okay. And now the statement you have a conformal field theory is the statement that you have the generating functional is well invariant. So you have a scaled metric and my sources. So delta has some wild weight. This will remain invariant if you have a scaled my sources j. Okay, yeah. It's j, but similar j. And it's also diff invariant.
The A here is an index on what? With us to dimension?
No, okay, I'm sorry. No. A is just a label that runs over all operators in your theory. So exactly, it's infinite dimension. It's infinite dimension because, as you will see, conformal field theories have an infinite number of operators. Even though we usually only care about the primaries, but anyway, you will know what I'm going to work. And for example, the thing that we will study, one thing that you can use this approach to do is to derive, even though we will find a more simple way to do it, but you can derive what the constraint of conformal symmetry puts in the correlation functions of operators, just by imposing that the functional is invariant under while and this transformation. But more importantly, what we will find is that generically this functional, so what is the statement that is well invariant? It's not as well invariant, the statement that, this is the statement that we will care about. The partition function is the same as this. Obey this relation. I keep changing the input. And then, so if this guy has dimension delta, then this J has to scale as D, sorry, here, as D minus delta. So O of X will go to omega minus delta A. O of X. So now for this to invite, I have to rescale my sources as omega delta A minus B.
You should synchronize between the sigma and the omega.
Because omega is like e power.
Yes, okay, so let me put omega squared.
But doesn't root G also? I mean, I'm not sure about the counting there because root G is gonna.
Right?
Root G is gonna go like omega power.
Yeah, that's why I have here.
4.
That's why I have here this.
Omega power D. Okay.
I have delta A minus D decided to cancel the metric. And the statement of anomalies will be that this will not be true. And anomalies are something that you don't need to go to curve space to identify them, but they manifest themselves very physically if you couple your conformal field theory to a curve background. And then we will see very explicitly what are the sources of the anomalies and understand them better. That's why I wanted to mention that this idea of coupling the field theory to the background metric. Okay, so hopefully I'll do the anomaly story either, well, not today, but maybe tomorrow or Friday. Okay, so that's, so any questions about this? So how, now what we've done is understand the kind of the geometric aspects of conformal field theory. Now we want to understand how these aspects are represented on the operator of the theory and on the Hilbert space of the theory. So maybe before we start, let me ask you, so which operators do you think are always present in a conformal field theory? And remember that we're just talking very abstractly, but from the things that you know about field theory and the things we discussed, which operators should always be present in a conformal field theory? Sorry? Operators. Which
operators.
Yeah.
Stress tensor.
Okay. Okay, so why?
Why? Because you have
You want to couple it to a background method?
Sorry?
You want to couple it to a background method?
translation.
Yeah, okay, that's a fancy way of saying it, but yeah. But just use the fact, by definition, a conformal field is a field that has those symmetries and the dilatations and so on, right? So it means that you have to have.
Translation.
Yes. Yes. So it's a phenomenon. You have to have the identity operator that has dimensions, and you have to have the stress energy tensor. What's the dimension of the stress energy tensor? Sorry?
I know.
Sorry?
The same as energy.
Think.
No, it's 2.
2.
So I just like 2.
Okay, why 2?
2.
Okay, so maybe this is something I should spell because if you're saying that numbers, there's a gap between. Yeah, so let's do it. So what are the things that we said are present in a conformal field? We had a conserved charges, right?
Yeah.
That were associated to translation, Lorentz transformations, dilatations, and spectral conformal transformations. Now these are the space-time transformations. Something that you can, that should not come as a surprise is that the currents. So by another term, any continuous symmetry has a conserved charge. And it wouldn't be surprised that the conserved charges associated with space-time transformations are all constructed from the stress energy tensor. So let's see that. Okay, but first to answer the, so first of all, how do you construct the momentum generator out of the stress tensor?
Contracting you have to refer transistors.
Okay, so
Here would be the general.
But, so using this, can you tell me what the dimension of T has to be? So that things make sense? Okay, so in field theory, to any global system, you have a conserved current. Okay? Good. And from a conserved current, you construct a conserved charge. Construct a conserved charge. How do you construct a conserved charge? Have you seen this in field theory 1? Yeah? Okay, so how do you do it? It's an integral over space, right? So of the zero component, right? That gives you a charge. And notice that this works because we compute now this is zero by using the conservation. Okay, so now again, can you tell me what the current associated to this guy is? To this guy is? Okay, particularly just let's say for energy, we use mu zero, right?
Yeah.
Okay. So what is energy? Energy is the integral over space. Zero. So this is energy. So this has to have mass dimension 1. This has, so this means, okay, so now I know what the dimension of T has to be. From this equation, you should be able to read it. D, right? D, because this has dimension 1, this has dimension 2.
But we should be careful with the index placement. Because J really wants to have an upper index, and T really wants to have mixed indices. And then it has dimension D. Because if you lower an index, then you have an extra metric factor, and this becomes D minus 2.
Let's be a flat space. We're a flat space. Like I'm phasing over the indices.
Okay.
Yeah. So this guy has dimension. And okay, so these are two objects that have to be in any conformal field theory. And the point is that the current associated to each of these guys, remember that we had these scaling vectors that depend on parameters. Each of the parameters were associated to each of these transformations. So we had something like a mu plus mu. So this was translation, it was rotation, then we had dilatation, and then we had special conformal transformations. Like that. And now you can wonder, stress sanitary test, for instance, is a basic object that tells you how, that has to do with space-time transformation. So you can ask, how do I construct the current associated? So to which set vector field, I have a set of generators. How do I construct the conserved current associated to this transformation? And the way you do it is you essentially contract the stress tensor with the Kelvin vector. And then you missing indices. Essentially, from here you should be able to prove that this is a conserved current. Using the fact that the stress tensor is conserved and trace it. Okay. So, but of course, interesting CFDs have many other operators other than this. And that's what we're going to study now. Okay. Any questions about this?
Is it possible to cancel while anomaly with diffeomorphism anomaly for some background matter?
But first of all, diffeomorphism anomaly only happens in very special dimensions. Okay, plus 2. I think the answer is I don't think you can. I mean, I don't know what it really means. But anyway, the diffeomorphism anomaly only happens in 4K plus 2 dimensions. Well, we will show either tomorrow or Friday. While anomalies can happen in even dimensions, not in those dimensions. There are dimensions in which you have one and not the other. But no, I don't think so. I mean, they have to do with different issues. One has to do with the non-conservation of the trait of the stress energy tensor. That's a wild anomaly. And the invariance has to do with the non-conservation of the stress tensor. We have something that's very important, is that one invariance implies, and I was implicitly using it there, one invariance implies that the trace of the stress energy tensor, okay, I don't know if you can see there. So one, so first of all, something that you know, okay, if you don't know, write it, is that if you look at the functional integral, there's the log, whatever, and you do a variation with respect to arbitrary metric variation, what you find is that the partition function changes in this way. Okay? This immediately tells you something very powerful about what are the implications of Wall invariant and deep invariant on the stress tensor. So if I impose, if the theory is Wall invariant, then delta G mu no is minus 2 sigma G mu no, right? And sigma is a completely arbitrary function of x, okay? So from here what you find essentially is that delta Z the trace times sigma. So this implies, what invariant implies that the trace of the stress tensor vanishes. Okay? While deep invariant so while implies the trace of the stress tensor vanishes, and deep invariant, okay, would imply that the stress energy tensor is conserved. So let's see it more explicitly. So let's, all that we need to do is plug in here what happens to delta G mu no under the diffeomorphism. So under the diffeomorphism, arbitrary diffeomorphism, what will happen is that you get, as I read many times before, this is essentially so this means that, and since since P mu no is symmetric, what this means is that you get something like and again, since psi mu is arbitrary, this implies exactly this relation. So, going back to the story, the statement about a wild anomaly will be the statement that the right-hand side will stop to be zero. And the statement about deep anomalies is that the right-hand side will stop to be zero. So they really talk to different physics. So the right-hand side, if you have a conformal a wild anomaly, the right-hand side will not be cancelled by any monkey business with deep anomalies. Because it doesn't know about the trace. It talks to different operators.
I mean, I was wondering if they can be captured by some parameter which is the same, and both of the statements are not true, but the theory might be conformal. So both the trace is not zero, and also the stress energy is not conserved, but you might have conformal in some very special case.
I would have to. My gut is that this sounds nuts, but I don't have to think more carefully. Okay. Good. So. So now what do we want to do? So now that we have completely understood what the conformal symmetry is, now what we want to do is to represent conformal symmetries on the operators, the ones that here that are creating gravitons. And just like in quantum field theory, in quantum theory, we look for, in that context, it's fields. Usually we think of them as elementary fields in the path integral. Here, remember that these always are not elementary fields in the path integral, these are abstract operators. That you need not think of them as being path integrated over. That's just this. You have a path integral, this would be some composite field, for example. Now we want to know how to represent conformal symmetries on such operators. But before doing that, maybe we should discuss the analog problem for Poincaré transformation. You remember that the conformal group includes the Poincaré group, okay? So here what we're thinking about is we want to give a representation of the Poincaré group on fields. Okay, so how do you do that? You have to assign certain transformation rules that will be compatible with the Poincaré algebra. And the way you do it, I think you know. So imagine I give you some field or operator phi here from X. First of all, okay, so maybe just to have more interaction. So which kind of quantum number do I have to assign to an operator or field in the Poincaré invariant theory to fully specify its transformation? Spin. So that the quantum numbers under rotation, right? So why is that?
Because suffix a little group per sign.
So people know what this word means? Maybe just say it briefly in case someone doesn't really know, but essentially what you want to do is define some operation essentially what those words mean is that if you know how the field transforms at the origin, and the origin is fixed precisely by the Lorentz rotation test. At the origin, the only thing that leaves the origin fixed is precisely Lorentz transformations. If I tell you how to represent Lorentz transformations of the field at the origin, and since translations obviously move the origin, I only have to focus on Lorentz transformations. Then the action of the rest of the Poincaré group is just fixed. Because if I know how phi A transforms, if I want to construct how phi an arbitrary other point X transforms, all I have to do is conjugate by translation.
In the argument for 5b, do you mean to put the inverse Poincaré transformation on spacetime?
Excuse me?
The arguments for 5b, should that be
The inverse one.
the inverse Poincaré transformation?
Yes.
Okay, because it's G right there.
So there's an inverse. Which here are you talking about? This one or this one?
So, okay, usually I denote it with, not like, I don't know, lambda plus A or something.
Okay, so yeah. So,
Since
okay,
G
so,
is combined.
so X tilde is Jx
Okay.
with A mu plus lambda mu. Okay, but one thing that is very important is that, okay, so there are two pieces to a Lorentz transformation, to a Poincaré transformation. There's a piece that acts on space-time, okay, right? Yeah, that acts on the rotation of the coordinate. You could call this the orbital part of the transformation. And then there is a part that acts on the Lorentz quantum number. We call this the spin part. The thing that is very important is that the way G is realized on the spin and the orbital part is in opposite directions. If this was not the case, it would not give you a consistent representation of the Poincaré group. You can try to say that if you put here G and you do two consecutive transformations, it's not the same as doing, imagine you do a transformation with G1 times G2. If you don't have this inverse here, and you try to do first G1, G2, or G1, then G2, you wouldn't get the same thing. So that's the statement that we have to represent Poincaré in a proper way. That's how you do it. Okay, so all that we have to assign for Poincaré is the Lorentz quantum numbers, because that's the only generator that fixes the origin, and then I can move away from the origin by a translation. Okay. So in practice, what this means is that is that under the such transformation, so I have a translation A and a rotation London, you know. What I have is that phi A of x so this is going to be a matrix. Okay. Okay, we're going to do it like this here. Hopefully it's not confusing. But for G, this matrix will depend on the Lorentz part, not on the Poincaré part, on the translation part. And then I'll have phi B. And this guy labels a representation of Lorentz. So for example, for a scalar, yeah, so now you have to supply a representation of the Lorentz group in the proper representation. So you have a scalar, the generators are trivial, you have a vector, the Lorentz generators in the vector representation. So these are the Lorentz generators, these are the representation labels. Would be something like no, here, right? This would be for the vector representation. R is a vector. For a scalar, it would be 0, right? And for a spinor, for example, up to factors would be the commutator of the diagram image. And again, you can now just convince yourself that if you do 2 consecutive transformations by G1 and G2, and you have this assignment rule, you have represented the transformation. Okay. Now, it's useful also to look at the infinitesimal transformation. What comes in the infinitesimal transformation, and then delta phi of x looks, which is again phi to the x minus phi of x. You have a translation part, and then you have what I was calling a spin part. Okay. So this is the part that just comes from here, from the translation. So this is the orbital. And this is the part that spins. That depends on the choice, depends on the representation under which the flip platform. Okay. Now you can, in order to convince yourself that this is a proper way of implementing, representing Poincaré on the field, you can now look at the commutator of 2 transformations that are labeled by 2 different parameters, delta 1, delta 2, B1 and B2, and compute the transformation of phi A. And what you find is precisely this, okay? Where B3 is precisely the Lie bracket of the 2 vectors. So this tells you that you have represented the Poincaré group properly. Any questions about this? Just to be quick before we get to conformal. Okay, so now we can try to do a similar analysis for conformal. Some way to say that's going crazy. Okay, before that, let's go back to this picture. So now we're in Poincaré. Now we could ask, using the same intuition, what labels do I have to assign to my field operator to completely specify the transformation properties of the operator? Can someone tell me? Sorry?
In Poincaré?
No, in the conformal. Sorry?
Probably the weight.
That's what? Why?
Because aside from the Poincaré transformations, you'd also have scalar transformations, which just guessing. I haven't really thought about it completely yet.
Actually, the logic is exactly the same as here. So the way you would do it is that you have translation. So translation allows you to move any point to any other point. So we just have to focus on the origin. Now, if you remember, what are the transformations that leave the origin fixed? So obviously, this guy is the origin fixed. Remember that also dilatation. Okay? So dilatation maps x mu to lambda x mu. So that tells you that in order to specify the action of the field, I have to represent not only Lorentz, but I have to represent the action of B. And actually, there's a subtlety. It turns out that this guy also leaves the origin invariant. That, I think, is pretty obvious if you think in terms of the inversion calculation inversion. So, naively, you would say that you have to specify 3 different quantum numbers: the spin quantum number, the dimension or dilatation quantum number, and the gas quantum number. And the reason that for the basic operators of the theory we set these quantum numbers to be trivial has, I'm just giving you a physical picture of why the basic operators are called primary, because the ones that transform simply also highest weights of the conformal algebra have these quantum numbers to be 0. And the reason is that remember that one of the things I was explaining yesterday is that that essentially you have B, you have P mu, you have K mu, and when we solve from the computation relation that this guy lowers the eigenvalue of D, while this guy raises the eigenvalue of D. Okay, because remember that D with P mu was plus and D with K mu was minus. So I mean that if you want to construct a representation that has energy bounded from below, so then the guy, which is called the highest weight, has to be inflated by K. This is exactly the same as when you study angular momentum. You have J3, J plus, and J minus. The primary, which is the state that's annihilated by K mu, is the analog of the highest weight state, Jj, that's annihilated by J plus. And then all other states in the representation are just built by acting with J minus, right, in the J2. Here they will be built by essentially acting with P. Okay. That will increase the energy. So this is just to say that in the conformal world, we have to assign for primary operators, for the analog of this one, 2 quantum numbers, the Lorentz representation R and the dimension R. Okay. And then you can construct any other operator in that representation, in the conformal algebra, just by acting arbitrary number of times with P mu. That's why the representation of the conformal algebra is dimensional, because you can act with P mu an arbitrary number of times. That's completely different than in this case, right? Because usually, this guy, if you act with J minus, you hit minus J and you're done. Even though there are complete representations of SU2 where you don't have to do that, but you don't want to know about that. Is at least the picture clear that what are the labels? So maybe to make this precise, I think that so the operators will have 2 labels. I don't know if I can hold the labels always, but for the time being, I'm going to say, okay, like that. And just to convince you from this theory, imagine I have this operator, and now I look at this other operator. So the commutator of, say, okay. Do you remember that one of them raised the energy, the other one lowered the energy? Okay, so maybe I don't have to do it. So I wanted to make more precise, and just using the commutation of D with P and K to show you that if I look at the descendant, so this guy will be a primary. So it's going to be initialated. The primary is an operator that's initialated when the operator is at the origin. So this is the definition of a primary operator. The descendants are obtained by acting with a raising operator, and this will be by acting arbitrary number of times. Okay, and this guy has dimension delta. If you now compute the dimension of this guy, of this operator, the descendant operator, so you'll find that this guy has dimension delta plus n. So even though the dimension of delta of a primary can be a priori arbitrary continuous number, the dimension of the descendants have a fixed gap, which is integer gap. Good. So this tells us how to do, and again, intuitively, now once you know how to represent the field at the origin, all that you have to do is conjugate now this guy by translation, and you will know how the operator transforms anywhere in space. Okay. So let's now write down the set. So now I can do a Conformal transformation from x to x tilde. So I think you know by now what I mean by this. So I'm going to call this g times x, okay? It's going to be a piece for the transformation that knows about the quantum number and the dilatations delta, that's the dimension of the operator. And then there is kind of a more boring, completely identical to this here, part of transformation that just has to do with Lorentz quantum numbers. Okay. So this actually is exactly the same as for Lorentz, with a wrinkle. Okay. Just to make it clear. Okay. Where R, okay, so first of all, the first thing is that this looks almost identical to Lorentz, except that, if you wish, this guy transforms as a density. Okay? So it has an non-trivial Cherenkov factor. And this R is the orthogonal matrix, the x-dependent orthogonal matrix that we constructed out of the Jacobian of the transformation. Okay? Remember that the conformal transformation was something like this. And we concluded that you can define a matrix, calligraphic R, you know, it's now x dependent. The omega inverse dx mu. It has the property that it's an orthogonal transformation. So R transpose eta R. Okay. So notice that all that I'm doing is doing exactly the same thing I was doing for Lorentz. Except, of course, except for Lorentz, the matrix that appears here, I erased it, was lambda mu, right? The measure of the Lorentz transformation, which is a constant Lorentz transformation. Here is the x-dependent Lorentz transformation. Okay. So this part is exactly the same as in the Poincaré group, just taking into account that you have to incorporate these wild factors. And then this is the length. One way you can derive this transformation also, by the way, that's why I also mentioned this wild plus this story, is that you know from general relativity how tensors transform the isomorphism. I told you how things that transform properly under well transformations transform under well transformations. So now if you concatenate a well transformation with the diffeomorphism, you'll get exactly this. So that's actually a way of deriving how things should transform once you know that how diffeomorphisms act on tensors and how well transformations act on operators. If you do that exercise, maybe the good exercise, you will recover exactly the same thing. Okay.
I mean, one other way of looking at this is that although scalars are diffeomorphisms, scalars are diffeomorphisms, where you can have densities that are like conformally there, in all generality. Scalars are different variants. So, but if you
But still transform.
but if you have wireline diff, then you can have even densities, right?
Yeah.
So that's more.
Yeah. So the point was that this factor comes completely from the well part of the transformation, but it has to do with that omega, and that omega. Okay, it's big careful here. Omega. Once you identify the well transformation with a compensating diffeomorphism, what you find is that this is the determinant of this Jacobian. 1 over t. So the density part of the transformation comes from the well part of the transformation. The diffeomorphism is just boring, they just do this. Okay. So now, for example, let me just again look at the infinitesimal form of the transformation. So now if I do infinitesimal transformation, then go to 5. Keep calling it 1, 5, 6, and less. Hopefully you know what I mean. So again, there is a purely geometric part. Let me write and then I explain the physics of this. Okay. So this is arbitrary conformal Killing vector. What you get is this transport part, the transform the operator and the translation, and the generated by the conformal Killing vector. You get a special dependent Lorentz transformation, the field part, and then you get this other, in general, x-dependent dilatation. Okay? And these quantities, sigma x, just so even though the local Lorentz, even though the special conformal transformation was something disgusting, at the level of the field, all that it really does is act as a local Lorentz rotation and a local dilatation. Notice that B, which was the guy that generated the special conformal transformation, the way it acts on the field is just like a rotation or a dilatation. Okay, this part. So nothing too exotic. And again, you can, to make sure that this is the right transformation, if you were not convinced, you can compute. To consider transformations and convince yourself that this is a proper representation of the conformal. Any questions? No? Okay, so now what I want to do, now that we have finally know how, another thing that's important to say is that even though primaries transform in this simple way, in a linear way, it means that, notice that the operators that appear here are the same operator back. Okay? If you look at the transformations, and the conformal transformations, the transformation of a descendant, Can someone tell me what do you expect will be different in this case? First of all, can you tell me tell me what will change in this transformation? Sorry? Okay, so delta will change because I already told you that delta increases by 1.
Yeah.
What else do you think can happen?
The points, space-time points.
Okay, recombination.
No, so this will not really change, right? It will be. Now, this guy, of course, there is a Lorentz
Right.
quantum numbers. You, of course, you change that representation to be that representation, but this doesn't change. The of course, those groups won't change. But what can happen is that for the descendant, the conformal transformation of the descendant can mix with the highest weight state. So it means that it will have a linear part, will be proportional to p mu for A. But then there can be a physical transformation, in fact, that couples to the highest weight vector. So it will be something like p mu for A. So that's why descendants, even though we know completely the transformation properties under conformal transformation, they're not as simple because they get mixed with operators that are one dimension lower than that. This is exactly, okay, so this sounds mysterious, but this is exactly the same as in SU2. You apply an SU2 transformation to a state that's not in the highest weight, it will talk to the guys upstairs and downstairs. But the key point in conformal filter is that even though you have these guys that don't transform as neatly, the properties of, once you know how correlation functions of the primaries, what the correlation functions of the primaries are, you, just using algebra, determine the correlators of the descendants. So descendants are very important in constructing the two-direct of the theory, but their dynamic is completely fixed by conformal invariance. That's why we focus mainly on the primaries, because the descendants, they're just facts that you have to carry around, but important facts. Okay, so I just wanted to mention that. And you can, of course, derive the transformation rules just knowing, using the algebra. And that's the point. That everything is determined from the algebra. Okay, so now what we want to do is, so the reason I said this is that now what we want to do is, as I said, you have two types of operators. You have primaries and descendants. As I said here in words, these guys are completely determined in terms of this. So now what I want to do is study the constraints that conformal invariance imposes on the correlation function of primaries. So let me go through that a little bit. Not too much detail because I mean, it's probably not good that I do arithmetic in front of you, but I just want to explain what the ideas of how you derive the constraints are, and you do it yourself. Okay, so what is the basic constraint that of conformal invariance on correlators? So again, you have a point x, you go to x tilde. You have an operator O, you go to an operator O tilde. Okay? The statement that you have conformal invariance is this. Is that if you take the transformed operator at the transformed point, the correlation function of these operators has to be the same as the statement that is the same. It's the statement that it should be the same as the correlator of the operator O pushed to that point x tilde, the same point x tilde. So this is the consequence of conformal invariance. Is this clear, the statement? You can derive this from many, many different ways, but I think the statement is clear that in order to compare two things, you have to compare two things at the same point. So all you do is you look at the transform field at the point and compare it with the original field pushed to that point. And this is exactly what this equation summarizes. So if you want to be pedantic, let me write this formula once. What this means is that these are the equations that you have to solve. this jump equals this. Here I just plug in the transformation this. That's all it is. So now you can go ahead and try to study the consequences of conformal invariant, starting from the simplest possible correlator, which would be the one-point function. Let's see what we get. And we'll see some miracles. So let's look at the one-point function, one operator, OS. And I guess for most of the analysis here, I'll focus on scalars, scalar operators, so I don't have to worry too much about this matrix part, which is annoying. Anyway, Lorentz invariance will kill the one-point function of a Lorentz invariant operator. So now we can start imposing this constraint for each of the different transformations in the conformal group. So of course, translational invariance implies that this guy has to be a constant. I think that's nothing, no one would be unhappy to say that. Another useful way to get an intuition about this is that you can take this transformation and do an infinitesimal transformation, and you will get, if you look at translation, what you should get is something like essentially the statement that A mu, D mu, acting on this guy is 0. Is that clear? How you would get that from that? Just expand those as infinitesimal and you will get this. Now, scale invariance. So now let's impose a scale invariant where x tilde is lambda x. This will imply that lambda minus delta c equals c. Okay. If I impose the dilatation invariance on this, given that already the one-point function is fixed by dilatation invariance to be c. So this implies, already it gives a very interesting result, that the one-point function of a primary operator is a constant only if delta equals 0, which is the identity operator, and it's 0 otherwise. So there are no interesting one-point functions in conformal field theory in the full spacetime. If you start doing interesting things like putting the system on a boundary, then maybe I'll leave it with an exercise. I repeat this exercise. If instead of studying the constraint on RB, you put on your spacetime a boundary at xd equals 0, say, and study what are the constraints of conformal invariance in studying the one-point function of x in this upper half plane. But what you should see is that now conformal invariance allows this correlator to be non-zero. And the reason will be is that putting a boundary does what?
It breaks
Some conformal transformation, and then it relaxes the constraint, and you can find something. Okay. Now let's do the two-point function. So for the two-point function, I think you will not be surprised that you will tell me what the constraint of Lorentz and scale, and translational invariant imposes on the two-point function. So let's now look at the two-point function. So Ox or Y. So what would translational and Lorentz invariant imply? Yeah, so the function of x minus y, or the distance. Okay, but now let's look at the scale variant. So here, how much this was known? Let me just do this one example more or less thoroughly, and then the other ones I need to work out. I mean, it's completely now clear what you're supposed to do. Again, this is only for scalars. Okay. So now I use the transformation rule under the dilatation. Under the dilatation, this guy goes into lambda minus delta 1, lambda minus delta 2, O y has to equal OX or y. So it means that, sorry, lambda. Sorry, you just have to scale this until the terms, right? So what this means that this is the same as f of lambda x minus y. Okay? So we get the constraint that lambda minus delta 1 plus delta 2 f of x minus y equals f of lambda x minus y. Okay? What does it imply? Tells us that f minus y has to be 1 minus x minus y to delta 1 plus delta 2. Okay? And this is what we expected. There is no length scale in the problem, so the only thing that you can have the correlators have is have some power law behavior.
Do you make constant in the numerator?
Of course, yeah. But we're not done. We have imposed scale transformation. We have not imposed number. We should impose a special conformal. So this is a bit unpleasant, even though it's really conceptually clear. It turns out that for this particular correlator, even though I keep warning you that imposing inversion is too strong in general for a conformal field theory, the theory is parity odd. You can verify that the constraints that conformal invariance imposes are the same as the constraints that inversion imposes, and it's easier to check inversion, of course. And if you work it out, what you will find is a nice little exercise. What this will tell you is that the
Why do you need to worry? Because inversion is Z2, so I have to do it twice if I have to represent a special conformal transformation. So even if the theory were parity odd, then
well,
it should still be special conformal.
no, but here I'm only the way I'm going to do that, I'm going to use inversion 1. Of course, if you use it twice, you have not getting it.
Yeah.
No, so here the cheat, if you will, is that I'm going to use inversion 1 and declare victory. But then the point is that if you do it a special conformal 1, you get the same. You get no further than the constraint. But of course, if you do the 3 of them, of course you do. But that's a mess. Well, no, I mean, you see, it's trivial, but I don't want to do it. So essentially, if you now impose a special conformal, what you will find is that the following interesting result, that this guy will be 0 if delta 1 is different than delta 2. So the two-point function of operators of different dimension vanish, and you will get 1 over x1 minus x2 to delta. Again, it can be, of course, a constant there. If delta 1 equals delta 2. So this means, so one thing that we learned here is that the dimensions of operators can be read off elementarily from the two-point function of operators in the CSP. And it is the subject of a set of critical phenomena to compute this number, because this tells you how thermodynamic properties scale as you approach the critical point. Okay?
So can I use inversion instead of special conformal for any correlator?
No, that's the point. No.
Just for 2 points? Or
Yeah, so usually for parity-even theories, it doesn't matter, because parity-even theories will include inversion, just if you have theories that parity. I can give an example in 3 dimensions, for example, of a particular tensor structure that can appear in a 3-point function that you would miss if you imposed inversion. But that's allowed if you only impose a special conformal. And that structure involves a tensor, the epsilon tensor, which is parity of. That's important. To just, it's important to keep it in your mind. Okay, so I think the pattern is clear. I will do the 3-point function, but now I'm not really going to do it. I'm just going to So okay, so maybe now that you have an intuition, can you tell me what you could write down based on Lorentz invariance, translational invariance, and dilatation? It doesn't matter, but let me just write the final answer. So here again, you have to, of course, translation and Lorentz information just tell you that you only have dependence on the distances between you have three distances here. Okay? Then scale invariance tells you that the overall dimension of this guy has to be the sum of the dimensions. Which is delta 1 plus delta 2 plus delta 3. Just like here, delta 1 plus delta 2 is the sum of the dimensions of the operators. And the special conformal actually determines completely the power structure. So here, let me put this, just to use the notation I used yesterday of this tensor, CABC. So the most general thing you can have is CABC times x12. So x12 means that this, the Lorentz invariant distribution 1 and 2 of delta 1 plus delta 2 minus delta 3. x13, delta 1 plus delta 3 minus delta 2. And x23, delta 2 plus delta 3 minus delta 2. Okay?
I have a question. Is this for arbitrary operators or just scalar operators?
Right now it's only scalar.
Okay.
You will be very happy that I don't really do tensors because actually I may do one just to capture a bit. So this, notice that the position dependence of the correlator is absolutely fixed. This is kind of amazing. Just like the two-point function was completely fixed. There is no other possible structure allowed. Notice that it is very different than if you have a scale invariant theory. In the scale invariant theory, the position dependence of the correlator is not fixed at all. You could have ratios of distances. That's a scale invariant quantity. But a special conformal doesn't allow that. They only allow this very particular combination. So as such that there are two invariant tensors in this game. Let's call it CABC for the three-point function. Here I could have called this GAB. And as I said yesterday, and you will see in detail next week, the correlation function of an arbitrary endpoint function can be constructed just using three basic facts. That you know the spectrum, or generally the two-point function, that you know the three-point function, and that you know how to capture the contribution of descendants, which are completely fixed by conformal symmetry. So from this, you can, from this data, you can construct any endpoint function. So now you can imagine what happens if I do a four-point function. Is it going to be fixed? And the answer is no. So of course the form of the correlation is constrained. But now what you have, now let's be in a, doesn't matter. Doesn't matter the details too much. What I want to say is that here you can construct out of these 4 points, you can construct two conformal invariant cross ratios. Okay. So you can convince yourself, this again is elementary arithmetic, that if I take I'm running out of time, as usual. First statement. Now that I have 4 points, I can construct these particular ratios of distances. And the first thing you can prove is that these guys are conformal invariant. Okay. What does this mean? Is that if I look at the constraints of conformal invariance input in the 4-point function, it will not constrain in any way the dependence of an arbitrary function of these cross ratios will satisfy all the conformal word identities. Another way of saying this concept is called word identities. So now all of a sudden, the 4-point function is not completely fixed by conformal invariance. There is an arbitrary function you have to compute. But again, you would know how to compute it if you knew the 2-point function, the 3-point function, and the sum over intermediate states that are fixed by conformal symmetry. Another point is that there is an interesting function that you have to go out there and compute.
Is there any good reference to see an example done?
Of
Calculation of 4-point functions.
Well, so this is what you will see next week.
Oh.
That's the whole point of next week is to use crossing symmetry to compute the 4-point function. I mean, these functions are complicated because so roughly speaking, the way you do this, you have 4-point functions and think it this way. It has to do with the operator product expansion. So what you do is you use the operator product expansion of two operators, and you expand them in a basis of operators. Another way, maybe a more physical way of saying it is that what you do is you insert a complete set of states. So you have a sum over all possible states in the Hilbert space. This is the same as summing over all possible operators here. The energy of the state will be given by the dimension. And then what you have is the product of two 3-point functions that gives the 3-point function of O1, O2, and the operator that appears here in the OPE. Likewise here. And now you have to sum over all intermediate states. This means summing over the primaries and all the tower of descendants that come with it. And one of the complications in this business is that the tower of descendants, even though it's completely fixed by symmetry, their contribution to the correlation functions are given by non-trivial special functions that capture essentially. What you have to, the thing you have to learn how to compute in some sense is, if you know the 3-point function of 3 primaries, how do you compute the 3-point function of 2 primaries and 1 descendant? Well, this can be get a bit nasty, you have to take lots of derivatives. Okay.
And when you insert the complete set of operators, are they normalized by some coefficients or something?
Well, yes. I mean, this, yeah. So,
okay.
If you wish, so this index was raised and lowered with the metric, with this metric. So if you do that if you normalize your 2 and 3-point functions, everything is fixed.
Will the sum converge?
Sorry?
Will the sum?
Yeah. So this is a very good question. The reason it converges in conformal fluid theory is that it doesn't converge generically in OPE of standard quantum field theory is the following fact that I have not fully explained. It's what's called the operator state correspondence, which means that is a one-to-one map between operators, primaries and all descendants, and the Hilbert space of the theory. And roughly speaking, the way that you can think of the convergence is the following: is that in quantum mechanics, and we're used to decomposing the identity as an infinite sum over intermediate states. So it's a perfectly convergent thing to do, and that's what we're doing here essentially. So the thing that makes the OPE convergent in conformal field theory is precisely the statement that is the operator state correspondence. This is just a standard sum over intermediate states that is perfectly convergent. Okay, I want to say something about tensors, but maybe this is too much. Okay, I'll leave it to an exercise. So, imagine now I want to complete the 2-point function of currents. So 2 currents. There are two covariant tensors. Again, just using show. Okay, what I want to do is to show using conformal invariant, the concept of conformal invariant, that this guy takes the following form. There's a tensor I mu x minus y divided by x minus y equal to delta. Where I is a very important tensor that I can write explicitly. So I mu nu of x is delta mu nu minus 2x mu x nu x squared. This essentially is the tensor, which is the Jacobian of an inversion. That's why we do with I, right? And has a remarkable property that it behaves as a connection. It transforms as a connection. And that's what you will need to use to prove this. So the basic thing that if you use this following property, which is straightforward to check, so x tilde is the action of inversion of an x. It has the following property. It transforms as a connection in the following sense. So if I make an inversion on this tensor, you get the tensor back with, so I don't know if you're familiar with like connections, but essentially you get a transformation by the same matrix at the point x and at the point y. So this allows you to transport, if you wish, pairs of points under inversion. And if you follow the same logic now just applied to vectors, you should be able to show that it's completely straightforward, but I don't want to do it. You can also do it for the one that's very important, of course, is the stress tensor. But again, the point here is that the right-hand side of the stress tensor will be completely fixed in terms by essentially concatenating these basic objects. Okay? So I is the right tensor when you have one component. If you have more, you just have to put them together. So let me just write the answer. So here will be this number Ct, which will have very important physical meaning, and has to do again precisely with anomalies. And then the position dependent is just completely fixed by conformal equality. Okay, this is x. Okay, let me put it at 0. Minus and so on and so forth. And you can follow the same logic by putting together in a pretty obvious way these I's to construct what the correlator would be for higher rank tests. And here, as I said, this is quantum number that we'll have to do conformal numbers that we will discuss hopefully tomorrow or Friday. There are more things I could say, but I shouldn't say them. You could imagine more complicated things when you have 3-point functions with one vector component, then you have to define another basic object, which is, so here we had I, there's a kind of a natural invariant tensor that you can construct out of 3 points that will appear when you have correlation of 3-point functions that depend on 3 points and one has one vector index. Okay. This guy, I'll just write it down. So you have 3 points, x, y, and z. This is the second invariant tensor that appears all the time when you constrain the correlators of 3 points that have a vector index, which is of this type. And now, essentially, the reason I want to write it is essentially now for all tensors, by suitably for any n-point function, by suitably combining I and this guy, you can constrain the correlator. Up to, of course, cross ratios. Those are arbitrary. Okay, so for another time, I'll stop here.